Welcome to our lesson on variations. In this lesson, we're going to look at combined variations or composite variations. We have already looked at the direct variation and indirect or inverse variation. So the composite variations, this is just terminology to mean that you have within one situation both the direct and indirect variation. Then we're also going to look at how variations can be interpreted graphically. So, like we have already seen, direct variation is of the form y varies directly as x, that is direct variation. Then indirect variation is of the form y varies inversely to mean the reciprocal of x, or inversely as x. So that will be the form of indirect variation. So for composite variations or combined variations, we can have one variable which varies directly and another variable which varies inversely. So for example, if we say y varies directly as x and y also varies inversely as z. So that will be written as a combined variation, where we'll say y varies directly as x and inversely as z. So in short, we multiply the inverse and the direct variation. We multiply the direct variation and the inverse variation when we are expressing combined variation. So we can say this is the same as saying y varies directly as x and inversely as z. So we can express this as a fraction of that nature to show that we have both direct and inverse variation in one situation. And of course, after this notation, we can get the equation in k, which is the constant of variation, and apply whatever initial conditions have been provided in order to solve for the unknown variables. So we can look at an example where direct and indirect variations have been combined in one question, which is an example of composite variation. So there's an example here where it says, given that y varies directly as x and inversely as the square of z. So we have y the question says y varies directly, so it varies directly as x, and then it varies inversely as the square of z. Inversely meaning the reciprocal of inversely as the square of z, so it means z squared. So this is the situation of our combined variation, which means our notation will be y varies directly as x, and we are going to multiply inversely as the square of z. So it means our notation will be like that, which we can simplify as y varies directly as x and inversely as the square of z. So this will be our notation, and we can introduce our constant of variation so that we generate an equation in k, which means we're going to say y is equal to k times x over z squared, which we can rewrite as y is equal to kx over z squared. So this is an example of composite variation or combined variation. So we have come up with an expression in terms of x and z and the constant of variation k for the variable y. Now the question proceeds to say the value of y is 10 when x is 32 and z is 4. So the value of k, we should find the value of k, the constant of variation. Okay, we are told when y is 10, y is 10 when x is 32 and z is 4. Okay, so we get that initial condition. Our equation of variation is y is equal to kx over z squared. So the question says y will be 10 when x is 32 and z is 4. When x is 32 and z is 4. So we can substitute this initial detail and find the constant of variation k. So where there is y, we put 10 and say equals k. The x is 4. Sorry, the x is 32 and the z is 4. So where there is x, we put 32 and z is 4, so it means we're going to have 4 squared. So say 10 is equal to 4 squared is 16. So in short, we have 16 into 32 is 2. So we have 10 is equal to 2k, which gives us the constant of variation k will be equal to 2. We divide both sides by the coefficient. So the constant of variation k will be equal to 5. We divide both sides by the coefficient 2. So we can rewrite the equation with the value of k, so that we say the equation is now y is equal to k is 5, so we'll have 5x, y will be equal to 5x over z squared. Okay, that will be our equation of variation. So we can use this equation to solve for the remaining part of the equation, which says, of course, part A, the value of k. So we have solved and we have found the value of k, which is 5. It's here. Alright. Then to find the value of y when x is 20 and z is 5. When x is 20 and z is 5. So the equation is y is equal to 5x over z squared. So the question now says we should find what y will be when x is 20 and z is 5. So when x is 20, when x is 20, z is 5. Okay. So y, we simply substitute, y will be 5 times when x is 20 and z is 5, which means 5 squared. So that will give us 5 times 20, that's 100. 100 over 5, which means y will be 4. So when x is 20 and z is 5, y will be 4. Then the last part of the question, we should find z when x is 9 and y is 5. When x is 9 and y is 5. So we'll have to use the same equation. We'll use the same equation, y is equal to 5x. Y is equal to 5x over z squared z squared. Now we want to find z when x is 9 and y is 5, which means where there is y, we're going to put 5 equals 5. Where there is x, we put 9. 9. So we are solving for z. In the formula we have z squared. So here it means we're going to cross multiply and solve the equation. So when we cross multiply here, we'll have 5 times z squared. That will give us 5z squared equals, that side we have 1 times 5 times 9, which is 45. So we can simplify here by dividing by 5 on both sides, so that we get z squared is equal to 9. Then we can get the square root of z, so that we have an idea of what z is. So we square root both sides, meaning z will be equal to positive or negative 3. So it means when x is 9 and y is 5, z will be 3. So that is how we solve combined variations or composite variations. And like I have mentioned, this can also be applied to graphs where we have the x and y axes used in order to interpret the variations.